Okay. So, now what we will do, we have already discussed about how to represent a particular vector with respect to another vector. Now, what we will do on this paper, which is a 2-dimensional, we already know, we will just take two vectors, one is x, the other one is y. Now, we will just do the same exercise, we will try to represent a particular vector, let us say any vector, let us say this is g. Okay. Again, what we need to do, first g needs to be represented by x, so we will be again putting a perpendicular and accordingly we will calculate c, or let us call that cx. Okay. G also can be represented with respect to y, so I will again put a perpendicular and I will get another value c2 or cy, let us say. Okay. So, two constant we have got. Now, I am trying to represent it with respect to these two vectors. So, what I do, I actually take both the vectors. So, basically I am taking a linear combination of these two vectorial representation. Okay. So, G earlier I was just representing with respect to some c into x, now I will do a linear combination. So, some cx into x plus some cy into y, and if we can properly minimize. So, right now we have just shown how to minimize that, but if you just put it this way and try to minimize it, you will see that as long as x and y are orthogonal to each other, you will always be able to completely represent this without any error. So, with 0 error, because what will happen if you represent by this will be your error. Now, this can be directly represented by this one. So, error will be further represented by the other vector, and then the residual error that is left, that becomes 0. Okay. So, the lesson that we have learned, that if you can, so two things, one is if you can, whatever dimension you have, the suppose vectorial space. So, this is a 2-dimensional vectorial space. In that vectorial space, whatever dimension you have, so it is a 2-dimension. So, two orthogonal vector to each other, if you can find out those two, any two. So, it does not have to be this x and y, I can represent G even by this x and this y, as long as these two are orthogonal to each other. Okay. So, if you can take any two mutually orthogonal vector, because the dimension is 2, with those two vector you can always perfectly represent any vector in that particular space. If I wish to represent it in 3 dimension, I need to have 3 vectors. So, that is why they actually represent it with respect to x, y and z. So, 3 coordinate you need or 3 vectors you need. Okay. As long as these, always you know that x, y and z are orthogonal to each other. So, all you have to do is you have to worry about the dimension of the space you are talking about, vector space you are talking about, and you have to worry about or you have to find out if the dimension is n number of mutually orthogonal vector. As long as you can do that, then you get a complete, we call that a basis set, and with those basis set, any other vector in that particular vector space, you can represent them without error. So, and eventually what happens, it is just a linear combination of all those vectors. Okay. So, this is a fantastic thing which has been already understood, and which is also, you are also familiar about this. Okay. So, you already know that this is how it should be. What we will now do, we will try to see if a signal, any general signal, can be represented by some constituent basis signal. This is what we will be targeting, and that is the basis of Fourier series. So, let us try to do that. Let us say I have a signal Gt. I wish to represent it with respect to some known signal xt. So, xt is a known signal. Okay. So, this is what I wish to do. Okay. So, I am saying that if only xt is there, like vector, I will be just multiplying it with a scalar quantity. Okay. So, I will say it is almost represented by this c into xt. Now, all we have to do similar thing. If I do this representation, of course, there is an error which is called the ET. So, therefore, I can write GT must be equal to CXT plus the error signal ET. So, ET must be, all we have to do is now minimize the error. That is what we have learned earlier, that in the vector we were minimizing it, there it was easier because we were just seeing where it becomes projection. There the error vector will be of minimum length. Okay. That means a measurable quantity. Vector, we are talking about length, and length is nothing but the second norm, that is the length square of vector. So, that is how we are minimizing the error. Basically, we are doing error length minimizing, that is what we are doing. Here also we will try to or target to minimize similar things. So, what we are trying to do is, let us say this GT and XT, they are defined over a time, let us say T1 to T2. Okay, so, it is a initially for simplicity we are saying that these signals are time bounded, it is only defined from T1 to T2, both GT and XT. So, we want to now minimize the overall error. So, what do we minimize? We have already characterized a signal, that is actually the energy of the signal. So, we will target to minimize the energy of this error signal. So, our target should be, let us calculate the energy of error signal, that should be integration E square t dt from T1 to T2, right. Now, Et we can replace T1 to T2 GT minus C xt whole square dt. Okay. So, this is what we are targeting to minimize EE. GT is a known parameter or known signal, or this is the target signal that we are trying to minimize. Xt is a known signal with which we want to approximate the other signal. Here, with respect to what we are trying to minimize, with respect to that C, think about that vector also, there also we are doing the same thing. We are trying to get an optimal C for which the error will be minimized. Same thing we will be doing over here. So, here we should minimize with respect to C, that means we will differentiate it with respect to C and make it 0, find out that value of C, that should minimize it. So, we will just devise this. Now, of course, the integration is over T and differentiation is over C, they have no dependency. So, I can interchange these two, right. So, I can take this things inside, differentiating G, suppose I open up this square. So, it should be G square T, differentiating with respect to C, that will be 0, then minus 2C GT XT. So, if I differentiate it, it will be just minus GT XT, right. I am differentiating with respect to C, remember. So, it was C GT XT DDC of C, because GT and XT does not depend on C. So, they will be coming out, it is just 1. Okay. The next is plus C square x square t, right. So, C square x square t should give me 2C x square t dt, this must be 0. Is this all right? So, I have just taken DDC inside and I started differentiating it. I know that T, GT, XT, they do not depend on C. So, those terms I have just opened the square and then started differentiating it. Okay. So, I have got this values. Now, if this should be 0, then immediately I can find out C, because C does not depend on the integration variable, that is T. So, I can write this as 2C integration x square t from T1 to T2 dt is equals to integration T1 to T2 gt xt dt. I can write this, or C becomes, is this fine? Oh, so there should be a 2, right, because it is 2 gt xt. So, there should be a 2, 2 gets cancelled. So, C becomes T1 to T2 gt xt dt divided by gt xt dt integration x square t dt. Okay. So, basically this is what I do get. Okay. That is a very important criteria. If now think about that vector analogy, when I was putting the vector thing, what was my C? C was dot product gx divided by dot product xx, right. Now, I can define my dot product over this signal space. So, the dot product now gt and xt, if I define my dot product as this one, wherever the signal is defined from T1 to T2 and then gt xt dt. Okay. So, if I define this as dot product, what happens immediately you can see all the things are getting connected now. If I now put xt, the dot product between x and x, that happens to be the energy of x. That also characterizes my earlier proposition that the way I was putting dot product is eventually in a vectorial space giving me the measurement, the distance of that vector. Here also the dot product is giving me the measurement that I have characterized so far, that is the energy of the signal. So, xt dot product will be T1 to T2 x square t dt. This is nothing but the energy. That is very good. The dot product in vector also gives me the measurable quantity, that is the length of the vector. Dot product defined by me over here also gives me the energy, which is the measurable quantity of a particular signal. Okay. From here again we can talk about orthogonality. So, when a signal will be orthogonal to another signal, when that similarly in vector, if I cannot represent a vector by another vector, then we say that these two are orthogonal, that means the corresponding C must be 0. Here also same thing, I have defined my C as this, okay. Or if I just write it one more time, so C is integration T1 to T2 gt xt dt divided by T1 to T2 x square t dt, which is nothing but dot product of gt xt, the way I have defined dot product, and dot product of xt xt, right. So, if C has to be 0, that means x gt cannot be represented by xt and gt and xt are orthogonal, then C must be 0. Immediately the condition comes that this must be 0. So, therefore, gt xt must be 0, or we can write gt xt dt is equal to 0. So, that is the famous orthogonality condition for a signal, right. So, this is whenever we talk about a signal, two signals xt and gt will be orthogonal to each other as long as this condition is satisfied. If the signal is defined from T1 to T2, then the multiplication and integration within that limit must be giving me 0. Okay. So, this is the criteria for orthogonality, and similarly we have seen the representation. Okay. Now, we will do some more things. So, whatever we have talked about right now, this was actually good for a real signal. We have talked about all real signal, and that is why energy calculation was easier, because energy is a measurable quantity, right. So, in a measurable quantity I want something real and I was doing a squaring and integrating it. Now, if I have suppose xt, okay, I wish to do this integration, right, T1 to T2 dt, this is my energy. Now, if the xt happened to be a complex signal, okay, which has a real part and an imaginary part. If it is a complex signal, then I do not have this evaluation, because then immediately I can see that Eg will not be a real number. So, to do that there is a way to do that. So, Eg I can define in this fashion. So, basically the definition of Eg then happens to be that if it is a complex, if it is real it will be just x square t. If it is complex, then I actually take that complex and take the complex conjugate of that and multiply that. Okay. and then I integrate. Okay. So, that is just a slight difference in definition. The energy definition for a real signal will be slightly different from the energy definition of a complex signal. But the thing is that because complex signal also captures the essence of means a real signal, same thing is happening over here. If it is a real, then it will just become complex conjugate is the signal itself, and if I just multiply, that will be just square, right. So, it just captures the other definition also, it is not away from that other definition. So, this is my energy. Immediately what will happen if suppose I have a, now the representation changes slightly. I have a signal Gt and I wish to represent it with respect to a signal Xt, but the only difference is now that this Gt and Xt are no longer real. Nobody has said me that these two has to be real. This can be now complex signal. Okay. So, now I will try to do the same thing, same derivation, little bit complex it will be, but I wish to again derive the similar definition for orthogonality for the representation of those C value, optimal C value. Okay. So, that is something we wish to do. Okay. So, now let us try to see what will be error. That is actually same thing, again Gt minus Cxt. Now, we have to minimize the energy of this error signal. So, the energy of error signal now, because it is a complex signal, and here even C can be complex, the coefficients also can be complex, that you will see later on. Okay. So, if that is the case, what we need to do is we need to take the complex conjugate, multiply it with error signal and then integrate over the limit, whatever limit it has. Let us say the limit is t or just t1 to t2, whatever we were writing. Okay. So, immediately it happens to be Gt minus Cxt okay. Now, all I have to do is I have to actually evaluate these things, and I have to, this is my energy, I have to minimize this with respect to C, but this is not going to be as easy as we have done. Okay. So, direct differentiation will not give me, because there will be C and its complex conjugate. So, I cannot differentiate it with respect to C. So, I have to devise another tool to minimize it. Okay. So, this is something we will discuss. So, now this EE, the way we have defined, I will just write it in this fashion. Let us see whether this is correct. So, T1 to T2 will prove that this is the correct representation, minus Ex is the energy of signal Xt. See why I have represented this in this fashion? It is because I want to minimize it with respect to C, right. These two part, if you see, these two part are no longer dependent on C. Okay. So, all I have to do is I have to somehow choose C so that this becomes 0. Okay. Then only I can say that this will be minimized with respect to C. So, I have just devised a separate rule for evaluating it, because direct differentiation was not possible. I was getting C complex conjugate and then differentiating with respect to C, that was difficult. Okay. But we have to first prove that this is actually the error square or error modular square integration. If you just keep calculating that, you will see that this is actually the same thing. So, basically if you just evaluate this part, okay. So, this you keep it as it is, if you just calculate this part. So, you have a this minus this modular square. Now, I will just write how to evaluate. Suppose I have a variable u and v which are complex number, I need to evaluate this. Generally we can write it in this fashion, mod u square mod v square plus, instead of 2 u v, it is written generally u v star plus u star v. Okay. So, this is how the complex numbers mean square of modulus of complex numbers are represented. Okay. So, if I just evaluate this portion with respect to this, what do we get? So, this is actually u plus v. So, this is becoming my u and this is becoming my v. So, just evaluate it, what do we get? Here we get c mod c square E x, right, because root E x is not a complex, it is an energy, it must be a real number. Okay. Then mod of this, okay. So, mod this square, so that should be 1 by E x, and then and modulus and integration, that has nothing to do, modulus does not have anything to do with integration. So, it will go inside. So, I can write T1 to T2 gt x star t mod square dt, right. So, here I think we have forgotten the dt. Okay. And then it is just u v star plus v u means u star v. So, u v star if you put, so what do we get? We get c root E x 1 by root E x, of course, there should be a minus, okay. And we have that same integration T1 to T2, but we have to put a star of that, right, u v star. So, star of that, so that must be g star t x t x star t, and its complex conjugate again will give me back x t dt. Okay. So, we get this minus, we get then c star root E x into 1 by root E x, and then we have this integration T1 to T2 gt x star t dt, right. Fine. Now, let us try to see if this is exactly equivalent to our gt minus cxt mod square. It is eventually, because what is happening, you can see this ex gets cancelled, this ex gets cancelled. Okay. So, what do we get? So, we had, let us see, we had T1 to T2 integration gt minus cxt mod dt. Okay. So, T1 to T2, right. So, we have, if we start evaluating it, so again we can, this square we can actually evaluate it with respect to u v mod square. So, this will be mod gt square and then plus c xt mod square, these two things will be coming, and then gt c star x star t, right, and there should be a minus, and then minus g star t c x t, right. And if you just see the previous one, it is just giving me the same thing. Okay. So, if you just see everywhere, I have this c. Okay. So, if you just match it, so what do we get? We have got, let us see, we have got this square. So, this square term, if you have evaluated, we have got this c square E x, right, which is actually x mod x square t, right. So, this term and this term, so this particular term and this particular term exactly matches, then our gt exactly matches gt square, and that term is also present over here, right. So, which is this term, that is already there. So, this term is matching, the next term is matching, this particular terms gets cancelled and the other two terms are already there, right. So, this representation exactly is the representation. If you just do it yourself, you will see that it is exactly the representation of this one. So, therefore, all we are trying to say that the representation we have put over here for EE, that is exactly the representation of that error mod square dt. Okay, so, no harm in doing that representation. But by doing this representation, immediately we can see that these two parts are free of C. So, therefore, all we have to do is we have to minimize this, or we have to make it 0. So, to make it 0, this inside term, if I just equate it to 0, I get my C, and that should minimize the whole E, because whatever else I do, this is a mod square term. So, any other thing other than 0 will actually increase the value of EE, because this term is free of C, this particular term, both the terms are free of C. If this term is anything other than 0, because there is mod square and addition, so it will always increase the value. So, the minimum value that I can get where this particular part is 0. So, whenever I put this particular part 0, immediately what do I get for my C calculation? So, C happens to be, so C root Ex must be equal to 1 by root Ex T1 to T2 Gt x star T dt, right. So, that must be the case. Immediately I can evaluate C, that is actually 1 by Ex integration T1 to T2 Gt x star T dt. So, for a complex signal, now you can see we have T1 to T2, only difference is earlier it was Gt into Xt, now I have a x complex conjugate T dt, this integration, and Ex can be written again as mod xt square or xt into x star T dt. So, now I can define, just redefine my, for a complex signal, my dot product as this, that suppose I have a signal Gt and Xt and I wish to do the dot product. So, dot product can be defined as this Gt x star T dt. So, this should be my new definition of dot product in a complex signal, and immediately if I take the dot product with itself, I get back the energy, no problem in that. And the orthogonality condition is this C must be 0, that means Gt must not be represented with respect to Xt. So, if C is 0, then immediately this dot product must be 0, or this particular integration must be 0. So, this is what we can see from our derivation. Next what we will do, we will apply this to actually get back the Fourier series representation.